You thought Neptune was a placid blue ice giant, a distant world shaped by cold, distant sun and settled by science decades ago. But the latest revelations, championed by Neil deGrasse Tyson and backed by data from the James Webb Space Telescope and Earth-based interferometry, show Neptune to be anything but predictable. In fact, it may well be the most exotic, volatile, and enigmatic world in our solar system, a world that rewrites the rules of planetary science and forces us to rethink how we define a planet. For decades, astronomers treated Neptune as a textbook case, a hydrogen-helium envelope wrapped around a layered core of ices and rock, a frozen orb warmed only slightly by residual heat, bathed in the solar wind, and sprinkled with violent winds whipping across its atmosphere. But the new Webb observations found regions of unexpected warmth, hotspots below cloud tops, where infrared readings spiked, highlighting internal heat sources unaccounted for in standard models. So Neptune isn't chill, it's surging from within. This internal warmth, trapped beneath layers of atmosphere, is reshaping how we view ice giants and their capacity to generate internal dynamics. If you're still watching, subscribe now. You crave more than answers. You seek what lies beyond. Subscribe now and be part of the few who never stop searching. Then there's the magnetic field. Neptune's field had always been an oddity, tilted at nearly 50 degrees and offset from the center. But now we know it's also erratic and fluctuating in ways that defy any known planetary dynamo model. In the standard view, Earth's molten iron core produces our magnetic field steadily. Even Jupiter's magnetic storm is driven by metallic hydrogen. But Neptune, its fluctuating, asymmetric field hints at a magnetic generator fundamentally different, running not on molten metal, but on flowing exotic ices and plasmas deep below. This begs another question. What if Neptune's interior is not a simple stratified core, mantle, envelope? What if it's a labyrinth of chambers, densities, cavities, high-pressure ice layers, perhaps pockets of plasma? Webb's gravitational mapping picked up subtle anomalies, small deviations in Neptune's gravity field, suggesting mass concentrations or voids, cavities not predicted by classical models. These might be pockets of superionic water, where oxygen forms a lattice and hydrogen roams freely, generating electrical currents and heat. If so, Neptune becomes a dynamic reactor, its interior roiling with heat, electricity, and mechanical turbulence. No longer frozen silence, but a living engine. That engine might also drive Neptune's famed winds. Those supersonic storms, whipping at 1,200 miles per hour, have been attributed previously to solar energy. But how does a planet that far from the sun generate the energy to power them? The answer now points inward. Thermal pulses from deep within, perhaps cyclical releases of built-up heat, are fueling Neptune's atmosphere. In effect, it's a planet whose storm systems are born on the inside, not from sunlight. Neptune grows its own weather from within. But perhaps the most radical shift comes from Tyson's suggestion that Neptune might occupy a new category, something between a planet and a brown dwarf. Brown dwarfs are failed stars, too small to ignite hydrogen fusion, but large enough to generate heat through contraction. Neptune is smaller, yes, but if its interior behaves like a mini reactor, supported by exotic ices and self-generated heat, perhaps calling it a planet sells it short. Maybe it's a hybrid, a bridge between planetary and stellar classification, one that challenges the rigid categories the IAU has used for years. Let's unpack the implications. Rewriting planetary formation. Neptune's unexpected internal dynamics undermined long-held theories of planet formation. Instead of evolving into a layered body of denser core and lighter envelope, it may have retained stratified pockets of high-pressure exotic ice, shaped by turbulent accretion or massive impacts in its youth. If Neptune can make and maintain a complex chambered interior with superionic material, what about exoplanets? Most mini-Neptunes and sub-Neptunes discovered by Kepler, TESS, and JWST could share similar complexity. That changes how we model their atmospheres, their habitability, their magnetic and thermal history. Planets we once dismissed as boring might be hiding turbulent, active hearts. Magnetospheres of moons and life. A shifting, unpredictable magnetic field creates a magnetosphere unlike any other in the solar system. Neptune's erratic magnetism may also affect its moons, Triton, Nereid, Proteus, creating varying plasma environments and radiation belts. These fluctuating fields might influence geological or cryovolcanic activity on these bodies. Could subsurface oceans behave differently under variable magnetic stress? Could life, hypothetically, find places to hide, survive, or evolve under fluctuating shielding? Atmospheric chemistry and climate. Neptune's internal heat pulses and exotic chemistry can drive atmospheric changes, creating temperature inversions, compositional shifts, or unexpected high-altitude haze. Dust storms, methane plumes, or odd spectral features might be driven not by solar variation, but by Neptune's internal dynamics. This would complicate our exoplanet observations. Those spectra we scrutinize for biosignatures and atmospheres may come with hidden internal drivers that mimic or mask life markers. Exoplanet classification crisis. A generation of exoplanet researchers has labeled worlds mini-Neptune, super-Earth, or sub-Neptune, often based on radius and density. But if Neptune itself defies layered interior expectations, then those categories may lump together wildly different worlds. Two planets of identical size could have diametrically opposed granularities, one with tidy layers, one chambered with exotic ice-driven dynamos. That requires not only a renaming, but a remapping of our taxonomies. Where will we go next? Neptune has never been visited by a flagship mission, only a flyby from Voyager 2. But these discoveries make it arguably the most compelling destination for a follow-up orbiter, or even a probe to sample upper atmosphere and magnetic fields. If Neptune is a naturally existing thermoelectric dynamo, studying it could revolutionize fields across physics, materials science, high-pressure chemistry, dynamo theory, atmospheric science. Would we design a balloon to float in its clouds, a sail probe to drop into its depths, or a radio array to monitor its magnetic oddities? Soon, a new Frontiers-class mission to Neptune may become as inevitable as Mars missions. A philosophical reset. Neptune reminds us how little we know, even about worlds we thought we understood. All those years we pictured a serene film of blue ice and nothingness underneath. But it was alive, active, an engine that warmed itself, spun itself, magnetized itself. It's a powerful reminder of science's limits and its necessity. We must keep reaching, keep testing, keep questioning our assumptions. It's not enough to observe a blue dot. We must peer beneath it, probe it, listen to its heartbeat. Implications for Earth. Neptune's internal heating, chambered structure, and storms driven from beneath offer possible analogues for Earth's own mechanisms. What if the thunderstorms across our planet are modulated by deep, unexplored pulses? Could our magnetic anomalies hold hidden melted pockets we don't yet account for? Neptune forces planetary scientists to confront whether Earth-like internal drivers could produce unexpected climate phenomena here, too, reminding us our dynamic planet is part of a broader planetary physics continuum. What sits next for discovery? Tyson and team emphasize that every advance in instrument resolution, wavelength coverage, and gravitational precision can tear holes in our assumptions. The Webb telescope's infrared gaze opened Neptune's heart. But the next prize may be sub-millimeter telescopes, LMA, probing deep composition, or orbiters with gravimeters and magnetometers to sense mass anomalies over time, or a probe to sample directly. Each new instrument doesn't just see deeper, it unveils new layers of complexity we didn't even know to expect. Neptune, once cast as a distant dot of cyan peace, is emerging as an energetic, mysterious, active, and fundamentally unknown world. With exotic interior chambers, dynamic magnetic fields, internal weather engines, and a possibly new planetary category bridging into brown dwarfs, it demands a complete rewrite of planetary science. More than just a curiosity, Neptune is a clarion call. Curiosity always demands immersion, not distance. Today it's Neptune. Tomorrow, the next obvious dot, a hot Jupiter, an ice giant, or rogue world, will demand the same. Each target we observe may conceal an utterly different physics. So let Neptune be our reminder. The universe loves to surprise. What we thought we knew will be upended. We must remain open to change, humble in our theories, brave in our exploration, and prepared to redefine what it means to call a world, a world. Neptune has not only challenged our models, it's redefined them. It reminds us how much remains hidden in the planets of our own cosmic backyard. And for that reason alone, Neptune may be the greatest surprise in modern planetary science. Kepler saw its signals. Webb confirmed its warmth. Now, the planetary science community must respond. Neptune demands understanding, not platitudes. And in the response to Neptune, we'll find the depth of our ambition and the breadth of what's still out there. The more we uncover about Neptune, the more it resists categorization. For over a century, we treated it as a quiet endnote in the solar system's lineup, a distant echo to Jupiter's grandeur, Saturn's elegance, and Uranus's peculiar tilt. But that image is collapsing. With every new observation, Neptune transforms from an afterthought to a centerpiece, an astrophysical riddle too loud to ignore. The James Webb Space Telescope peeled back layers that had never been touched by human eyes. It revealed not just a planet behaving oddly, but a planet whose behavior can't be reconciled with classical planetary science. That should alarm us, or excite us, or both. Let this then start with Neptune. Fixed heat. In theory, Neptune shouldn't emit much energy. It's far from the Sun, receives only 0.1% of the sunlight Earth gets, and it's been cooling for 4.5 billion years. Yet, Neptune radiates more than twice the energy it absorbs. Even more curiously, it does so more efficiently than Uranus, which is nearly identical in size and composition, and yet gives off much less internal heat. That discrepancy has baffled scientists for decades. Now, with new data, there's a working theory, and it's radical. Neptune may contain self-regulating internal heat pumps, zones where thermal gradients trigger sudden pulses of convective energy, rising through the dense interior in quasi-periodic surges. These thermal pulses, guided by resonant cavities or stratified chemical zones, may fuel atmospheric winds, magnetic field distortions, and infrared anomalies detected by Webb. In essence, Neptune may be internally oscillating, like a planetary heartbeat. If true, that raises major questions. How stable are these pulses? Could they scale into planet-wide upheavals? What triggers them? Are they thermodynamic cycles, phase changes in supersonic ices, or the result of quantum behaviors under megabar pressures? Let's go deeper. The possible presence of supersonic water behaving as both solid and liquid under extreme pressure, has vast implications. In this state, oxygen atoms lock into a crystalline grid, while hydrogen ions flow freely through it, carrying charge like a metal. This exotic form of matter may exist in Neptune's middle layers, serving as a conductor for electric currents and helping to generate its magnetic field. But what if supersonic ice isn't just present? It's dominant. In that case, Neptune might not be a gas-ice hybrid, but a slushy metallic sphere wrapped in clouds. That would explain why its magnetic field doesn't behave like Earth's or Jupiter's. The source isn't a spinning iron core, it's turbulent, chaotically flowing plasma-like ice, where fields emerge and collapse like ripples in a stormy sea. That storminess extends to Neptune's magnetic poles, constantly shifting, not aligned with the rotation axis, and prone to sudden asymmetric flips. Earth's field takes thousands of years to reverse. Neptune's might do it in decades, or even less. That kind of volatility suggests not a stable dynamo, but a chaotic attractor, where flows shift in response to minor changes in temperature, composition, or pressure. This isn't set just academic. If Neptune's field shifts rapidly, so do its auroras. Unlike Earth's polar glows, which follow a relatively fixed pattern, Neptune's auroras could dance across hemispheres, strobe unpredictably, or even vanish for decades before reappearing somewhere else. That's what Webb may have glimpsed: infrared hotspots, correlating with intense, shifting magnetic disturbances in the upper atmosphere. Now consider Neptune's winds, some of the fastest in the solar system, exceeding 1,300 miles per hour. They don't just howl, they persist, forming massive storm systems like the famed Great Dark Spot, which appeared, disappeared, and re-emerged elsewhere. For decades, We assume the sun's meager rays help drive these patterns, but that no longer adds up. With internal heat confirmed, the dominant hypothesis is now internal thermal weathering, convective bursts rising from deep within, hitting the base of Neptune's atmosphere like undersea volcanic eruptions. These could inject sudden energy, spin up localized vortices, and then dissipate or migrate, depending on the surrounding pressure zones. Picture it. A planet where storms rise from below, not fall from above. A place where the weather is born in the belly of the beast. But the greatest implications may not be confined to Neptune alone. We've long used our solar system as a yardstick. Earth is Earth. Mars is rocky and dead. Jupiter and Saturn are gas giants. Uranus and Neptune, ice giants. Simple categories, made for textbooks. But with Neptune's revelations, those boxes no longer fit. What if most exoplanets labeled as Neptune-like are actually radically diverse? Some may be like traditional models, gas layers over icy cores. Others may have slush metal mantles. Some may pulse with internal fusion events, brief as lightning. Others may be more like mini brown dwarfs, failed stars with thermodynamic inertia and magnetic fields powerful enough to sterilize nearby moons. It gets worse, or more intriguing, when we realize we've only ever glanced at these planets, spectra, transits, radii, but the inside? Pure guesswork. Neptune is the one chance we have to open the black box. That's why Tyson's remarks carried such gravity. Because Neptune is no longer just an ice giant. It's a boundary case, a liminal object that straddles planet and something else. If it generates heat more like a brown dwarf than a planet, shouldn't we ask whether its classification is flawed? Does a mass threshold still define a planet? Or should internal processes, like heat generation, fusion onset, or field symmetry, dictate where one category ends and another begins? Maybe Neptune is the prototype of a third kind. Not terrestrial, not Jovian, but something in between. A deep thermodynamic anomaly, a churning relic of early solar system violence, an unlit fuse that under different circumstances might have burned like a star. And this might explain another mystery: why Neptune and Uranus, so similar in mass, are so different in behavior. Uranus spins on its side. Neptune does not. Uranus has weak weather. Neptune rages. Uranus is dim. Neptune burns. Some suspect a cataclysmic origin, a massive impact that rearranged Neptune's interior, injecting energy that still hasn't dissipated. If so, it was more than a collision. It was a recreation, a planetary reset. What hit Neptune? And when? Was it a rogue protoplanet, a failed core from the inner system? Could it have originated beyond the solar system? And if such impacts were common in the chaotic early days, how many other planets across the galaxy bear similar scars? These aren't just questions for Neptune. They're questions for planetary genesis as a whole. And they sit urgent. Because as more exoplanets emerge from the data, giants, dwarfs, tidally locked infernos, cold blue marbles, the labels we use are breaking down. Super Earth, hot Jupiter, mini Neptune. What do those terms mean? If Neptune itself is no longer what we thought, Tyson's argument is clear. We must shift from size-based classification to behavior-based analysis. Mass is not enough. Composition is not enough. We must consider energy systems, field generation, structural volatility, even evolutionary potential. A planet isn't just what it is, it's what it does. And Neptune does a lot. Even from 30 astronomical units away, it reaches across the scientific spectrum into materials science, dynamo theory, atmospheric physics, quantum chemistry, and even metaphysics. Because ultimately, Neptune is a mystery of limits. The limit of what we can see, the limit of what we can simulate, the limit of how we define a world. And as Tyson reminds us, science isn't about defending definitions, it's about challenging them, replacing the map when the terrain proves it wrong. Neptune is the terrain. The map is now obsolete. So what comes next? We build new models. We fund a dedicated mission. We send orbiters, magnetometers, Probes. We drill into cloud tops. We model supersonic behavior under gigapascal pressures. We ask better questions. We listen to Neptune, not just observe it. Because the most dangerous assumption in science is that the unknown is unimportant. Neptune proves the opposite. It states the unknown that changes everything.